Hello. This is the STC audio slide presentation presenting the topic, Bayes detection for additive white Gaussian noise model. Basically, in real-world situations, the data we transmit is affected by numerous, unwanted signals, which we term as noise. This corrupts the information contained in the transmitted signal, either by adding data to it or by reducing the information present. So, this calls for a device that needs to retrieve the information transmitted at the receiver, by removing the effects of noise. This device is called detection block and the theory associated with it is called detection theory. Signal detection theory. The detection block will consist of two sub-blocks. One that compares the data with a fixed threshold and assigns it to either a 0 or 1. And next, a logical detection block that provides logical correction to the data obtained from the first block. For example, if we transmit a 1 and detect a 1 at the receiver, then we have a hit. If we transmit a 1 and detect a 0 at the receiver, we have a miss, because the data sent is missed. If we send a 0 and detect a 0, we have successfully rejected the data. If we send a 0 and detect a 1, we have false alarm. So, the wrongly detected data has to be penalized for a better performance. We must have a better detection system to minimize the penalty. Bayes detection theory. We now define a method called Bayes detection, that deals with the prior probability of the sent data. For this technique, we consider our received data Y to be a part of an observation space R. Bayes detection divides the observation space into two regions, depending on the threshold calculated using the cost function. The decision rule is defined as follows. Del of Y equal to 1, if Y belongs to gamma 1. And equal to 0, if Y belongs to gamma 1 complement. Conditional costs. Thus, we calculate the conditional costs, the cost R0 when 0 is sent and the cost R1 when 1 is sent. R0 equal to C10 into P0 of gamma 1 plus C00 into P0 of gamma 0. R1 equal to C11 into P1 of gamma 1 plus C01 into P1 of gamma 0. The costs C00 and C11 can be considered to be 0 because they are correct detections. Combining the conditional costs, the Bayes cost is given by R of delta equals pi 0 into R0 of delta plus pi 1 into R1 of delta, where pi 0 and pi 1 are the prior probabilities. We have to obtain the optimized decision rule, which involves obtaining the threshold from a factor called likelihood ratio. Likelihood ratio is obtained as follows. L of Y equal to P1 of Y, divided by P0 of Y, for Y belonging to the region, gamma. Thus, combining the equations, the minimized decision rule can be obtained by minimizing the Bayes risk as defined. The region gamma 1 is defined as gamma 1 equal to Y, belonging to gamma, such that P1 of Y is greater than tau into P0 of Y. We can define the value tau as tau equal to pi 0 into C10 minus C00 divided by pi 1 into C01 minus C11. Hence we get a relationship using the likelihood function from which the threshold can be found. Hence, the Bayes detection rule is as follows. Del B of Y equal to 1 if L of Y is greater than tau, else 0.
Now let us consider the model of additive white Gaussian noise. Suppose we transmit zeros and ones in the form of a signal. We represent a 0 and a 1 by fixed numbers mu0 and mu1, such that mu1 is greater than mu0. So, the signal received at the receiver will be of the form Hj equal to mu plus epsilon, with j equal to 0 or 1 and epsilon is a Gaussian random variable, with 0 mean and variance sigma squared. We know that adding a constant to a random variable will affect only the mean of the random variable. The constant becomes new mean of the random variable. Hence, the observation is distributed around two different locations. This leads to the hypothesis being written as H0, where y is given by Gaussian distribution, with mean mu0 and variance sigma squared, and H1, where y is given by Gaussian distribution, with mean mu1 and variance sigma squared. The Gaussian distribution, or normal distribution, is defined with mean mu and variance sigma squared. As mentioned earlier, the Bayes threshold is obtained by finding the likelihood ratio. Therefore, the likelihood ratio is given as L of y equal to P1 of y divided by P0 of y, which is again equal to exponential of mu1 minus mu0 divided by sigma square, whole multiplied by y minus average of mu0 and mu1. Thus the Bayes test is given by del B of y, which is equal to 1 if L of y is greater than tau, and 0 otherwise, where tau is the appropriate threshold. Since mu0 is less than mu1, the likelihood ratio is a strictly increasing function of the observation y. So, comparing L of y to the threshold is equivalent to comparing y itself to another threshold tau dash, which is equal to L inverse of tau. If we rearrange the terms, we get del B of y equal to 1, if y is greater than or equal to tau dash, and 0, if y is less than tau dash. Here, we have an illustration of testing with Gaussian errors. And in this case we consider uniform costs and equal priors. And hence we obtain a symmetric distribution such as two Gaussian curves centered at mu0 and mu1. Since we are considering equal priors and uniform costs, we get the threshold as given by the equation of tau as mentioned. For example, with uniform costs and equal priors we have tau equal to 1 and tau dash equal to the average of mu0 and mu1. Thus, in a particular case, the Bayes rule compares the observation to the average of mu0 and mu1. If it is greater than or equal to the average, we choose the region specified by H1. If y is less than this average, we choose H0. The minimum Bayes risk for this problem can be computed if we have Pj of sigma 1 for j equal to 0 and for j equal to 1. It can be obtained integrating the area under the Gaussian in the region from the threshold to infinity. Here psi denotes the cumulative probability distribution function of a random variable. If we consider the particular case of uniform costs and equal priors, we get the minimum Bayes risk in terms of cumulative probability distribution function. When the minimum Bayes risk is plotted as a function of t, we see that the performance improves monotonically as the separation in means, mu0 minus mu1, increases relative to the standard deviation of the error. The quantity d is a simple version of signal-to-noise ratio. We are now going to present an example application of how Bayes is used in detection. We have used images to represent the detection algorithm for easy visualization. The input images were converted into binary image applying an threshold. White Gaussian noise was added to mimic the effective channel. Bayes detection was applied to the received images. This is Rajnikanth, as you all know. This image is converted into a grayscale image pose as values from 0 to 255. We apply threshold as 127 on it, to convert into a binary image. The binary image presented here has zeros placed at 0 and ones placed at 150. The prior probabilities are calculated from this image. And we add Gaussian noise with mean 0 to the input. This image represents the data corrupted by the channel, due to transmission. Finally we apply Bayes detection rule on the corrupted image to detect the transmitted image at the receiver's end. This picture represents the detected image applying the threshold. The rule seems to have performed reasonably well with minor glitches visible here and there. The threshold was found to be 127.55. This is the comparison of the transmitted and received images. The output might change if we consider unequal costs.
This slide contains the results when Bayes detection is applied to another image, to which white Gaussian noise of zero mean and variance 36.6336 is added. The original image is shown and its binary equivalent is displayed next to it. Bayes detection is applied to the noise-added image and the output obtained is almost equal to the original binary image. The threshold used for the image is 129.09. This slide contains the simulation results of Bayes detection of a transmitted binary sequence with white Gaussian noise of zero mean and variance 0.01. The threshold for Bayes detection is -0.00075. The result contains the input to binary sequence, transmitted sequence, Gaussian noise, received signal with added noise and Bayes detected output sequence. Conclusion. Hence, Bayes criterion is one of the detection techniques, and this requires the knowledge of prior probabilities and conditional costs. There are other methods to obtain good performance in detection. They are the minimax criterion, which is applied for Bayes costs with unknown prior probabilities. The method deals with finding the prior probability for which the Bayes cost remains fixed, so that the cost remains the same, even when the prior probability varies. The Neyman-Pearson technique, which involves the use of a randomized decision rule, for a given probability of false alarm, in the view of increasing the detection probability. This method does not require the knowledge of conditional costs,